Let's just tinker around and learn about random matrices and enjoy ourselves doing it. And so my usual approach, you can understand an area but through one of two methods. You can either read the literature on it, or alternatively, you can pick a problem and try and solve it. Now, if you do that, my advice would be, if it's a totally new area, find someone who knows this area really well and try to work with them rather than go out on your own. But if you can do that, you can solve a problem in a particular area, and you do it properly, then you will have definitely learned something, and that's good. And so this, for me, was dabbling in matrices. Now, there's a book by Verdú and Tolino, and they cover a lot of ground, but where you see applications of wireless to random matrices. But of course, this area has only recently come out, and only amongst a small number of people, of random Vandermonde matrices. But it turns out that, these abstract mathematical ideas do have relevance to wireless systems, and when we get there, I'm going to spend a minute or two thinking about that. But let's before we go anywhere else, let's admire a random Vandermonde matrix. Here it is, and so you can see I've got L columns, and I have n rows. And if you like, you can make L equals n, and 1 over root n is just gives me a sensible scaling. So, for example, central limit theorem type scalings work with this. And then I have thetas. And of course, these thetas, this is the random part of the matrix in here. And they could have any of a number of distributions, but they'll be concentrated on, say, minus pi. Now, if you look at this matrix, of course, it's familiar to you. And the reason for that is because it looks just like a discrete Fourier transform. And if we chose these values, evenly spaced, yes, you would get a discrete Fourier transform. But of course, we're not going to get that because we have these thetas at random. Now, when we do choose the thetas, I'm going to prefer to choose them with a distribution that has a continuous density, usually over the entire interval. But so this is the object that we're going to play with. It can be generalized, and I'll try to indicate how to generalize that. But it's nice to think of it as a random Fourier matrix. Now, what we're after. Remember, I'm standing as I just like this thing. I like to look at this object, but it's nice to learn that what that use is. So now what we're going to be concerned about is the limit eigenvalue distribution of these random matrices, and we're going to do so under the conditions that we're going to have a selection for the phase distribution. If you like, let it be uniform. Don't worry too much about it. You can just choose them uniformly. That'll be fine for the moment. And then we have this ratio of the columns to the rows. And if you find that inconvenient, please think of it as 1. But in general, we won't want to do that, but it's convenient just to get the flow of things. You can just think of this matrix as being square. And then this is that scale factor. Now, when I talk about random matrix and random eigenvalue, let me say what I mean by a random eigenvalue in this context. For the most part, what I will mean is that I will first of all draw the matrix according to this distribution. I will then form V star V, and I will calculate its eigenvalues, and I'll throw them into a bag, and I'll scrub them on the bag, and I'll pull out an eigenvalue. And that eigenvalue, that is my random eigenvalue. So that's how I obtained it. And
Phil, I'm sorry, the star simply means adjunct, right?
Absolutely. Complex conjugate. Yeah.
Is there a need for L to be not larger than n?
Interesting point. No, there is no need. It can be larger than n.
Does L vary in any specific way? Only that we require this limit.
So from the point of view of understanding our asymptotic exchange, we need this to be true. Okay, so why is this important? It turns out that there is a wireless channel model. I mean, you guys know a lot about wireless, of course. So, but this is the so-called ULA model here. So you've got mobiles at various angles, and then you've got these antennas are equally spaced, and then under kind of plane wave variables, you can calculate the field here, if I'm not mistaken, and you can show that this arises as a Vandermonde matrix. In fact, we'll look at this if we have time later on in a bit more detail. So that's the first case, the ULA model. You may not feel that's a very realistic model of wireless, but never mind, we nevertheless have it. Now this one, however, this problem here I'd like to spend a bit more time on, because I feel it is something that you might want to look at in more detail, and this is this one. So this precedes us. So this is a multi-dimensional signal processing problem. And the idea here is that you're going to chuck sensor networks. So I'm going to roughen your board a bit. You're going to on a line, or perhaps on a square. Let's chuck them in a square, although it's a generalized. The idea is you throw points at random. Now I'm in 2 dimensions, but you could be in 1 dimension if you want to think about Vandermonde. And this represents these regions. And then the idea here is you're measuring some field, which we'll say is in 2 dimensions. It's in D dimensions in general. And it takes measurements here. And then what one is trying to do is estimate the Fourier coefficients that determine the field from the sensors at these points. And then, of course, one could, by the usual means of interpolation, estimate what the field would be throughout the area. So you can think of this as an example of kind of random field measurement. And now the phases, which correspond to the position of those sensors, they're entering again in as the let's call them the Fourier matrix entries, but randomized. Now, so these people have looked at this question. I have a copy of their paper here, and what they were particularly interested in was the minimum mean square error estimate for the Fourier coefficients, and what they showed is that, for example, for the Vandermonde case, that essentially it depends on the distribution that I'm talking about, which will be in 1 dimension, of course, like this. It would be something like this. It would go alpha, beta over lambda, let's say beta, where this is in my notes, that's C, if you like. This is C. This is the ratio of columns to rows in the Vandermonde, and then there's another alpha C here, and it's expectation over yes, this distribution. Okay, the very distribution on the eigenvalues is determining the minimum mean square error.
What is alpha there?
Alpha there. What is alpha? Good question.
Is it a random variable?
No, it's a constant.
Lambda C is there.
What is alpha?
I guess C is what you described before, right?
It's the ratios, yeah, but what is alpha? Now I have to look it up. Yes, is alpha. I think it might have something to do with the noise, but I can't find it there. I can see it in their notation. Alpha corresponds to an equation in terms of the filter. So there's a cross correlation, G dagger D. G dagger D, like this. V, which is my minimum estimator, alpha is an offset. So it's a parameter that's being used in the construction of the MMSE. So it's under, I suppose it's under.
Right. What is D over there?
D is the dimension of the field. So D equals 1 means we're scattering things on a line, and then we're estimating the Fourier coefficients using linear MMSE. All right. Okay. Now I already described this. How we're choosing our eigenvalues, but once we know we're choosing our eigenvalues like that, we realize that at least for finite realizations of the matrix, we can calculate the moments of the distribution by looking at the traces. So that's very nice. So one way of accessing a probability distribution is through its moments. And so we learned that if we take the trace L must means divide by 1 over L, and we take the expectation, then we wind up calculating the moments of the eigenvalues. I mean, imagine this thing is written out, is diagonalized, and then you can see that, in fact, this will be lambda 1 to the n, through to lambda n to the n, and then we'll be selecting uniformly between those, and therefore that quantity therefore, and then the averaging is with respect to the selection of the matrices, and that will give us our moment distribution for our eigenvalues. So that's very nice. So we have a link between the matrix and the moments of the eigenvalue distribution for finite n. But in fact, here it comes. DUN is, for example, uniform, and so we see that this is what we're thinking about. So we have access to the moments of this distribution. Now, it's of course nice to have access to the moments of the distribution, but the fact that the moments do not exist at n does not guarantee that in fact we have a limiting distribution. But in a way, we don't want to work with this horrible n in here. We're hoping that there will be some asymptotic properties of the distribution which will gain us insight, just as in other areas people like to do asymptotics. So in fact, we want to do that here. But to do asymptotics, we have to know that the limiting distribution exists. And we don't know that. All we know is at the moment that we can work out these moments via these formulas here for finite n. So one object has to be to somehow or other work out what these moments are, and then to show that as n goes to infinity, we have some kind of well-defined asymptotic distribution. So we're interested in that. Right, so now in order to do that, we have to do something kind of complicated with the traces. And so the idea is that if you look at the trace sum, you can characterize the trace sum by considering partitions. And what you're going to do is, instead of working out each term in this expression, instead of working it out all in one go, that's too much. What we're going to do is we're going to take special sums, which are subsums of this, and we're going to work those out, and then when we add them all together, then we get the actual moment. So we want, these are called the cumulants, but they're not the usual classical cumulants. Let's call them for the moment the cumulants according to this partition. So we have a partition, of course there'll be lots of those, of the set 1 through to n, and once we've partitioned to various sets, and here we have k blocks or subsets, every point going into one of these, then we have a mapping, and all that mapping is going to do is, if you take a particular point in n, it's going to tell you which block it goes into. So this I has gone into block R, and this whole process is being done so that we can start to work out the moments. So now you can see how we're breaking up the trace. So we're doing things from the bottom up. We're learning how to view these matrices in ways that we can think about. And so this is nice. We're just thinking about sums here. And then instead we break the sum up into partitions, and then we sum over each partition. And then our hope is that we can say something about the expectation with respect to partitions.
So what is A, L1, L2? Is that a submatrix or an entry in A?
So A is the matrix itself. L1, L2 is an entry. And for our purposes, this will be, I think, V dagger V or V star V is A. I've just written it in terms of that. All right. So now let's do some partitioning, and we'll start. So now, if we do a partition, then we can define these things. For various reasons, these equations start to become interesting. Let me just throw them in. You can see that what they are is they're simply linear equations. There's no constants, and you've got the blocks on the left and the same block on the right. So this is the equation for the jth block, and this is kind of going into the block, and this is in the block. There, you've got these sums, and it turns out that this sum here corresponds to the calculation we want to do for the Vandermonde matrix, namely take a partition, take the expectation with respect to that partition of the trace for the number of points we're looking at, let's say n, then this quantity here, the volume of this solution set, turns out to be the number that we want over here. So this equation here, when we're calculating the Vandermonde moments via these partitions, the individual values are determined by these. So this is the cumulative, if you like, that corresponds to that partition here.
Is that a typo? Are you having both VJs on both sides?
Yes, I am.
Yeah.
So this is somehow EJ is the event that BJ, the partition, has this property.
No, this isn't random. This is.
It's a definition of an event. That's a colon. Like EJ is such that it's an event that this is true.
No. This is a space, a linear space. It's part of the hypercube, and then here is the solution set, and here it's its volume. Right, so it's.
Okay, so far this
a geometrical
definition of EJs has nothing to do with anything.
No, it's
Just the
no
definition of
events there.
something.
So, no events there. No events there. No, it's a geometrical object. It's defined by this. It has this volume. It has to be said that Ryan and Deborah preceded us in this. You can find their paper in Transactions on Information Theory. So they show all this and look at things that way. I think it came out about 2 years ago, 2008, something like that. Right. But anyway, never mind. It turns out these partitions come in two kinds. So the one on the left is known as a non-crossing partition, and the one on the right is called a crossing partition. And these things are well known, very well known objects. Although they were new to me when I first got it. Now it turns out, if you write down a partition for the Vandermonde problem, and it's a non-crossing partition, then the answer is 1. So all of those are gone. Unfortunately, most of the partitions, and you can count those, are crossing, not non-crossing, and there the answer is different. It's not 1 and it's not 0. It's somewhere in between. And so here's the partition here. So we're blocking out. You remember it's 1 and 3, and then 2 and 4, and it goes like this. So here are the equations, and so we can now set about this task of working out volume. So we now want to find out the volume of this lot, such that we satisfy this equation where we've thrown away one for the export variable. So we throw that away, and we'll find that the answer to that. Oops. Well, I hoped it would tell me what the answer is. Oh yes, there it is. It's 2/3. So then, and in fact, that's how the rest of these factors go. They are not 1, they're not 0, they're somewhere in between. But one has to just calculate away. One get a general formula. I'm not really in possession of that. All right. Now the number of partitions of a set is well known, and in fact it is the Bell number. So, and this is the Bell number, which is of course a unit. It's the nth moment of the unit Poisson. That's because we have k factorial, e to minus 1 over k factorial, and then we're taking the expectation of k random. So that's nice. The Bell numbers are expectations are nth moments of unit Poissons. Now, if you want to know what the number of non-crossing partitions, that's termed by the Catalan numbers. So that was the left-hand set of partitions, and of course the other ones, they make up the rest. So the Catalan numbers, unfortunately, are quite a small fraction of the total. All right, now, so Ryan and Deborah, as I mentioned, they preceded us by in doing a lot of the groundwork in this area, and so they proved that the limiting moments exist. So, and they're doing this under this slightly more complicated situation, where we have these matrices d rho. And I think I'll just let you. Joint limit distribution does not mean in the sense of probabilities. I think I'm going to let you read Ryan Deborah's paper, and I'm not going to burden you with worrying about those. So we'll just throw the identity in there, and that'll be much happier. And then we'll wind up with this limit here. So then we know that the moments are going to some number. Ryan and Deborah have shown that. And again, if we take C here, and we take a distribution nu, then this limit is given here by the classical cumulants. So it's just as I described. If we set C to be 1, D is just going to be 1 as well here, then all we're going to do is sum up the classical cumulants. Now, another thing Ryan and Deborah showed in their paper is, let's suppose that we start with the uniform distribution, and we work out all these cumulants here for our limiting eigenvalue distribution for the Vandermonde, and we do it for the uniform. Now suppose that we have some other distribution, say P of x. What would be the cumulant for that? And the answer is that it would be this quantity here. So it means that once we've done the hard work of working out cumulants for the uniform case, now we can work out the cumulants for arbitrary continuous distributions with this density. So that's nice to be able. That means that we once we have in some sense, if we understand the uniform case, we can work out the moments for other cases too. So Ryan and Deborah, they went on and they showed these various properties, which we more or less discussed now. So the cumulants between 0 and 1, k rho is rational, k rho equals 1 infinitely if non-crossing. Okay, so on we go. So this k rho is the Vandermonde expansion coefficient. We know what that means. So, for example, if we follow through on everything that we thought about, and we want to work out the fourth moment of our limit distribution, then we know our Catalan number, 2n plus 1 n times some powers there. That's going to get that 14 of the partitions are non-crossing, so that's 14 ones. And the 15th, as we've seen, is actually is a crossing partition with 2/3. So the total moment then is 14 and 2/3. That's the fourth moment of the Vandermonde coefficient. Right. And we've also seen this, that we have this link between the probability distribution here and the Vandermonde expansion coefficient for k rho. So now, in some sense, this is the smallest. And the reason for that is that if we apply Jensen's inequality to this problem, then this density comes here, we wind up with this inequality. So in fact, the cumulants for other distributions of the densities are larger because of Jensen. Interestingly, Ryan and Dever spent about half a column showing that result. But in fact, this is all it is. It's just okay, so now, so we took a look at this, and one thing is that you can in fact calculate the coefficients in another way. Here are the partitions coming up again. Here's the mapping. So you can, if you've got the partition, you can write down this quantity here, which is in terms of sinc functions, perform this integral, and again you get the expansion coefficient k rho. So again, we can calculate it there. All right. So for example, if we take the example that we looked at earlier, which is for rho equals 4, for n equals 4, then yes, that gives us the right answer for that 2/3. And in general, you can get that. And we also showed that, for certain types of partition, say this partition, we get here, we can show that that corresponds to this integral here. So we can even start to get asymptotics on these partitions. And this is going to come through as a consequence, I think, of the central limit theorem, but I'm going to hold back on a little bit. But something like that is at work there. All right. Right. Now, now an important point is that Ryan and Dever showed only that the limit moments exist. But actually, it's important to know that the distribution exists, and it's not enough that the limit moments exist for the limit distribution to exist. For example, the log normal has all its moments, but there are other distributions than the log normal which have the same moments. So just showing that the limit moments exist is not enough to show that the limit distribution exists. But in fact, in this case, we can argue via the method of moments. And the method of moments tells us that provided if the moments satisfy some property, in other words, they are distribution determining some sequences of moments do have that property, then there is a corresponding unique limit measure. So in fact, the moments that we're looking at here satisfy Kalman's theorem, and therefore the limiting distribution, there is only one distribution with that sequence of moments. And then using the methods of moments, we can then show that the distribution itself is of the eigenvalues is converging to that, and that means that the limit distribution exists. Now we know that. All right. Now, so the measure exists, and that's by Kalman's theory and the method of moments. Now, the other thing we try to do is, I think this is just establishing, this is just establishing this result. So I'm getting up, but what I'm doing in order to apply Kalman's theorem is I'm actually calculating these quantities and bounds on them in terms of, I think this is the Bell-Nun's number here to the power 1 over 2k, and then I'm getting this estimate here, and then this estimate is in fact what's getting me to Kalman's theorem. There's an equivalent theorem in Feller's book that does nearly as well as Kalman's theorem, and if you applied it here, you would draw the same conclusion, namely that this distribution was determined by its moments. It's just slightly weaker condition. But anyway, so we can converge, we can conclude that the limit distribution exists. Now, another difficulty with the Ryan and Dever results, if you will, is that they only showed that the existing moments existed for densities which are bounded. So of course, if we want to apply this theory, we want to consider the possibility of densities which are unbounded, of which this is an example here. So it turns out that for distributions like this one, we can show again that a limiting eigenvalue density exists. So the new feature is that this density here has bounded moments, but it's not in L1. Right. Now that function is given by this density here, and what's important about this density is that this is the characteristic function of this, because it's symmetric, is real and convex. So this function, this probability density function, has a real and convex characteristic function. And because of that fact, we can show by looking at integrals and various other things that the moment limits exist again. So there are examples of distribution densities, therefore, which are not bounded, but for which the limit distribution can be shown to exist. Unfortunately, there are other densities like this one, where the moments will not exist for all values of little n, and therefore we have no means of showing whether or not the limiting eigenvalue distribution exists. So in this case, the first two moments, I think, exist here for the limit, but not beyond it. And therefore we do not know, because our analysis is based on the existence of the limits of the moments, we simply do not know in this case whether or not there's a corresponding limiting distribution for the limit of Vandermonde matrix. All right. Okay, so those are the things that we looked at on the limit distribution of the eigenvalues. So if I were to summarize that, I'd say that we showed that for a broader set of densities, the limit distribution exists, and we obtain results for additional results for the cumulants. We do have a conjecture on the size of those cumulants, but we only succeeded in proving that conjecture for a small number of cases. Never mind. Let's keep going. Let's see what else we can find out about this. So let's now look at another problem in connection with this matrix. In particular, how does its maximum eigenvalue behave? And note that in the case of the maximum eigenvalue, there's no need for a limit distribution. We can think about the behavior of the maximum eigenvalue, whether or not there's a limiting distribution for the bounders or not, and that could be useful in applications. So let's look at that. And we note that the maximum eigenvalue could be as large as n. That's the largest it can be, and that corresponds to the Fourier case. But what we want to know is what is the behavior of this maximum eigenvalue as a function of n. So now, where does this come up in applications? I feel it comes up in, for example, the maximum eigenvalues are coming up where matrices are applied to these compression problems, for example, and one is interested in what the maximum eigenvalue would be. So let's see if we can get a handle on that. Now, in working with this matrix and knowing its relationship to Fourier expressions, it's not surprising to see this quantity coming in. This is the Dirichlet kernel, which is well known to be related to Fourier analysis. And by fiddling around in a simple way with this matrix here, we can show that this matrix has the same eigenvalues as this matrix, where these are the random phase differences that we're using to generate it. And this quantity, let me call it the Dirichlet kernel. So one way to understand the maximum eigenvalue, therefore, is to look at this matrix here, and then see if we can understand it from there. Okay, so in fact, we have, for the maximum eigenvalue, we have upper and lower bounds on it. And this bound is the upper bound. And it's telling us that the maximum eigenvalue is not growing much, it's growing at about the size, at most, of log n. So although if all the values were, spread out like a Fourier, separate, evenly spaced, we might get n. Typically, we're only going to get this as the size of the maximum eigenvalue at most. So there's an upper bound. Now, how was it obtained? Well, it uses a Chernoff bound type argument. And so what has been done, in short, is that each row has been scanned across, and then because for each row, the theta k for that row is held fixed, and as we scan across, all the thetas are independent, we can construct a bound for the size of that row. And now we repeat for each row, but we notice that, of course, these are dependent random variables, so that we apply the union bound on the maximum row size, and that gives us a bound on the maximum eigenvalue. So that's how that's being obtained, and that gives you a logarithmic value. So we know it's not growing any faster than log n. But what can we say that, in some sense, it's growing? The rate of. Can we say something about the rate at which it must be growing? So we'll look at that in a moment. But note that was proved for the case when the PDF is bounded. If it's unbounded, like the one that I was looking at earlier, where I think we had a half here and a half here, then it blows up much faster. And in fact, we can show that it's going up at n to the alpha, which is certainly faster than square root of n. So log n. So that estimate.
So somehow you get this is very different.
Yeah, this is different, and that's because
like was the one uniform, the first one?
Yeah, the first one is uniform, or more generally a bounded density. So this one was bounded, but this one here is not infinity. So this does not satisfy that condition, and therefore, and in fact grows this fast. Okay, it's not hard to show that. All right, now let's go to the case. Now we want to know how fast is the maximum eigenvalue. And this problem actually was very interesting. I solved this problem by the sit and stare method. So you may have used this method yourself. What you do is you put up a simulation of what it is of interest to you. You've thought about it in your head and nothing seems to be working out. So you, in sheer frustration, throw it up on the computer and you stare at it. And you hope that inspiration will come to you. And unfortunately, in this case...
That contradicts your opening statement.
Right. It does. Well, I'm in trouble now. I'm sorry, but I was a desperate man. Desperation, one may have to abandon one's principles. So I look at, you can look at whenever it gets small, you can look at the eigenvectors and they're occurring in a particular way. And that tells you ultimately that this will be the correct bound. Now, why? Why is that? And the answer is that remember that this matrix back here is being determined by this beast here, the so-called Dirichlet kernel. So if you MATLAB a Dirichlet kernel, it goes like this, it oscillates rapidly like this. And you know that the thetas theta differences are effectively determining, theta k minus theta l is determining where you are on this Dirichlet kernel. and you're looking for big eigenvalues, and it therefore looks as though you want the to be somewhere in that range in order to get what you want, and that's right. So now, if we think about that picture, and we think about thetas, let's say it's a square matrix. We're going to throw n of these thetas onto that real line, and we want to get the maximum eigenvalue actually. So how are we going to do that? Well, the argument is as follows. The first thing we're going to say is, let's pick any submatrix of this matrix. Because the matrix is symmetric, you'll notice that if I put theta L and theta K here, it's saying it obeys the interlacing theorem. So the interlacing theorem tells me if I take the maximum eigenvalue of any principal minor, let me say, of the original matrix, then that will lower bound the maximum eigenvalue of the full matrix. That's the interlacing theorem. So now all I've got to do is find a subminor matrix that works well, and the subminor matrix that will work well is when I get this thing to be 1. And to do that, I want the thetas all to be more or less the same. So now all you do to complete is you take this and you break this line up into 1/n blocks, and you throw the thetas in as balls into those urns, and you look for the urn with the most number of balls in it, and that will give you your ones to within some small value here. So that's what you're going to do. So this whole question, to answer it, amounts to answering the question, if you throw n balls into n urns at random, how many balls would there be in the urn with the maximum eigenvalue? And it turns out some Germans actually solved that problem recently, and the answer is that it's order log n over log n. It's the answer to that. But I mean, you don't. So that result is easily accessible. You don't really, although the Germans do more in their paper. It has to be said than simply sticking out. But you can access this by considering Stirling's formula and asking how does the maximum of a bunch of Poissons. And you will come to, by looking at the asymptotics, you will come to the same conclusion here. And if you want to link the balls and urns model to a Poisson distribution, please do the following thing. Just throw into those n urns just shy of n balls per urn, say n times 1 minus epsilon balls into there, but according to a Poisson value, so that there's a random number of balls, so it could in fact be n. Now the distribution is precisely Poisson. Now overthrow, do the same thing, and you'll be able to argue that in fact the maximum in those two experiments is very little different from the maximum you get with the more strict version, if you will, of the experiment. And so you may as well work with Poissons, and now you can do it. So that's all you need for the German argument, and that will give you all this estimate here as well. So that's very nice. Oh, and here it is. This is just what I was telling you. Just a balls and bins argument. All right. Then let's now think about the problem at the start of the talk. Here for the Tolina and Verdú, for Gaussian type matrices, we have statements about the eigenvalue distribution here, which are very clean. We get these results, and we get a limiting capacity. And the question is, can we obtain the same for this case? So in this case, we have D is now the spacing here between the antenna elements, lambda is the wavelengths, and then we're getting this expression here. So this is a Vandermonde construction again, but with a it must be with this distribution thrown in here. So then we can show that in fact the limiting capacity of that network, we know that the limiting distribution exists from our earlier arguments. We can now show that it's given by this quantity here we're limited. We're integrating over the limiting measure for the eigenvalues. So that shows that the capacity, limiting capacity of that system.
So what is gamma there?
Gamma is your SINR. Yeah, gamma is the SINR. So it's unit noise.
Am I reading this right? That this says essentially you get the same kind of growth of capacity that's linear in the number of antenna elements kind of on each side.
Yes.
So you're dividing by the number of dimensions, and you're taking capacity dividing by n and showing it.
Yes.
Okay.
Yes. Yes. All right. So now this is this mysterious distribution. So if you actually simulate it, and so you take some enormous matrix V, this time with 1,000 by 1,000 matrix, form V star V, get MATLAB to work out the eigenvalues for you and plot it, then you get a picture very much like this one. You can see there are various peaks in it. The distribution, actually, you can show that it's concentrated on the entire real line. What's less clear is whether there is an atom at the origin. In other words, so we can't easily tell that from moments. So is there an atom at this point or not? Or indeed, are there atoms? We don't know. But we are indeed actually looking at that.
So an atom at that point means that you get a bunch of zero eigenvalues with strictly non-zero probability.
Exactly.
Right.
Exactly right. Let me say that if that is the case, whatever the probability is of getting that string of zeros, it's very, very small. We know that, but we don't know that it's zero. It must be small. Yeah, that's right. Of course, in a realization, we get no non-zero zero eigenvalues with probability 1, but in the limit, yes. Get that. So this is the upper band. This was the logarithm that we were looking at earlier. And here is the lower bound. And this, in fact, is what the simulation does. So you can see that it's coming up very slowly indeed. So the log, for my money, the log n of a log n band has caught it. So even at n here, you can see it's not really come up very much. So the maximum eigenvalue of these matrices, therefore, does not grow very fast. Now, so we are continuing to answer questions. The first one, does the limit distributor have atoms? No one knows that. Can we find a lower bound for k rho? We have a conjecture for that. Here is our conjecture. We proved this for very small values of k up to 4, but not beyond it. And yeah, I guess that concludes my talk, except, for example, that just to say that as I mentioned, we are looking at these results in the generalized eigenvalues that appear in the multi-dimensional signal processing paper. So we have been able to obtain results for those too. And additionally, beyond that, we're also getting results for the minimum eigenvalue. Not whether it's an atom, but how fast the minimum is going to go to zero. I mean, it's certainly faster than 1 over n squared, but we think it must be much faster than that. So I'll stick my colors to the master, and I think it's going down to something like e to the minus root n over n in that case, for various reasons.
Thank you.